For starters, something that hasn't been discussed too much recently, that was brought to my attention that I should talk a little bit more about, is what stud means. Well, there's two parts to stud. The first is the letters themselves are shorthand for standard. The second is this colon colon. That's called a scope resolution operator. And we'll take a quick look at what that means with an example. So we can create a namespace, so say stream, and then inside of that we can make some struct. So say OBS. Now, if I want to access that struct outside, I have to go stream OBS. So the colon colon lets us unpack the namespace. So just like here, everything is in the standard namespace. So when I say like standard vector, we're unpacking vector out of the namespace. The reason that this feature is available is that I can, in another namespace, create another struct called vector. And now I'm able to differentiate between stud vector and stream vector, so I can use similar names without the names interacting, which is very good for library development. But today, we're going to talk about three main design patterns. The first is event observer, the second is state machines, and the third is the entity component system. So let's get started with event observer, and we're going to start our patented hello world. So we're going to go int main, std out, hello world, std end out, and we already should have a CMake script here. It will include IOStream, give that a quick build, give that a quick run, we get hello world. So we're going to create a brief emulation of a main loop. In the last video, we showed how to draw a triangle with OpenGL, and in that, we talked about creating the main loop that renders a new frame every time. So we're going to emulate something similar like that. So we're going to go std out, setup. So this will include an emulation of a whole bunch of stuff, model loading, everything we need to start up our game. And we're going to say while true. Remember from that video that we want to have something more useful here, like not Windows should close. But for our emulation, just saying loop forever is fine. And then remember, we also want to clean up after ourselves. And then we're going to drop down a counter, size underscore ti equals 0, I for index, how many times this loop has run, and we're going to print out frame I. Frame I plus plus. And if we now give this a run, we should get a whole bunch of frames counting up. So let's go and quickly add in the ability to add a few events that get called at the start of the frame and at the end of the frame that we could then subscribe to. So to start creating events, you have to go back to the last stream where at the end we talked about a delegate. And if you recall, a delegate is a special type of resizable array or vector in C++ parlance, which stores an array of functions. And in our case, they're just going to be void functions. So in order to use vector, we have to include vector. And in order to use function, we have to include functional. And the syntax here is how you would write a function type. So we have the return type and then the list of parameters. So right now it returns nothing. We could have it return an integer instead. And we can have it take an integer and a string, or nothing, like in this case. Events tend to not return anything. We don't really know how to process the return from multiple functions at once. And then, depending on what they do, they may or may not take something. So say a wave event might take the wave number as an input. So delegates inherit from vectors, which means that they bring in all of the behavior from a vector. The ability to add, push back, pop back, resize, stuff like that. So we're going to add one more bit of functionality, void call. And what this is just going to do is going to go for each function in this delegate. And notice that I'm taking a reference so that I don't copy the functions. We're just going to go function and call it. In order to make this a little bit easier to use, we're going to go void operator parentheses, so it takes nothing. The double parentheses is a little bit weird. This is operator parentheses, and then the parameter list. And all this is going to do is just call. So we're now going to make two delegates, the delegate frame start and frame end. And at the start of the frame, we're going to call frame start, and we're able to just call it like a function since we overrode the parentheses operator, and frame end at the end of the function. If we run it, nothing should change, but we can now add other things that we weren't aware of when we created these to the delegate. So I could go frame start dot pushback and then some fake function. This notation is what we call a lambda. It allows us to define a function without giving it a name, and it also allows us to capture state. I can say I here, and we'll capture whatever the current state of I is. So as an example, we'll capture I, and we can instead see out I is, and we'll print out I. Now, when we run this, we'll see before every frame, it says I is 0. Well, why is I 0 when we can see that's going up? Because we captured the state of I right here. We can instead capture by reference, and you'll see that it'll then track the values instead of just a copy. But this is very useful for things like waves in a tower defense, or like a bullet impact, or a button press in like a UI system. Any sort of thing where we don't know ahead of time what behavior we want to happen on an event. And what's extra cool about this is not only one thing happens, we can push back as many handlers, is the word for them, for the event as we would like. So that is the event observer pattern. The next pattern of use is called the state machine pattern. So we're going to model a state machine for player behavior. So we're going to assume that we're making a platformer game. So what can happen? The player can jump, the player can attack, the player can idle, and the player can fall. We're going to add a little bit of nuance to this, and we're going to say that the player can only jump while they're idling. So we can go idle to jump, and the player can only attack while they're idling, and then the player can only fall while they're jumping. The idea here is we have these two actions that we can take while we're idling, so we're not doing anything. And then once we've jumped, we start falling, and we can attack. So how might we go about representing this? Well, we learned that enums are a great way to store a state. So we're going to make an enum for our state. So what do we want? We want idle, we want jump, we want attack, we want fall. And now we need to start setting up what do we do when we're in a state, and what do we do to transition between the states. So we might go if some variable state equals idle, then we can check for input. And if input equals base, then we can go and set state equals to jump. And if input equals left click, then state can be set to attack. So we've defined some conditions if we're in this state that will allow us to transition to a different state. We can do another, else if state equals jump, we can go if falling, then state becomes fall, and so on. Else if state equals attack, we can play an animation, and else if a state equals fall, we can check if on ground, then we can go state equals idle. So you get this kind of machine that changes what we do depending on what's happening. But using this bunch of nested ifs has a couple of problems. One is all the repeated checks is kind of slow. We can use something called a switch on the state, which will make that part a little bit easier. A switch is almost like a for, but it has to take a number or a number-like thing like an enum. Remember that an enum is secretly just a number behind the scenes. When we hover over, we see idle is 0, jump is 1, attack is 2, and so on. So a number or a number-like thing, and that checks which number is the state currently set to and jumps to this. So it's like an if statement, but we don't have to check everything in a line. We can just go straight to the correct answer. The other problem is this gets kind of difficult to work with. So what we often do is create more of a structured method of these states. So we're going to go struct state, and we're going to define what's called an interface. And the idea here is we're going to say, I have a couple of functions that can exist. So what functions might be useful? Well, a transition into function might be good. Transition into. So if I want to do some sort of action when I transition into this state, this might be called. And then maybe a void process function that gets called every frame. And maybe a void transition out of function that gets called when we end. So now I'm going to introduce a new keyword called virtual. I'm going to go into more detail about how virtual is implemented in the future. But for the purposes of right now, all we need to know is that a virtual function does not have to be defined here. We can define it in an inherited struct, and it will figure out which version to call based on the inherited struct. So instead of defining it, we can just say equals 0, and that tells C++ that we want to define this virtual function later. So where do we want to define that? Well, we're going to make a new struct, jump state. And now, what do our functions do? So we need to create our functions, and we have this little new keyword called override, which ensures that there's something to override. And you notice that it's complaining that there isn't because we didn't mention that we are inheriting from state. A jump state is a state, and it has all of the functions of state. So what did we do when we transitioned in? Nothing. What do we do when we transition out? Nothing. But what do we do when we process? Well, every frame, we checked if input, which doesn't exist in this example, equals space, then we can go some transition function, and we would like a void transition states new state, and we'll define what that does in a second. We're going to transition to jump, and if input equals F click, then we would like to transition into attack. And we can create similar versions of this state that does that. So now the part that would be useful is actually being able to track the current state. So there's a couple of ways to do this. So the way we're going to be handling transitions is we're going to take a state pointer, S, that goes along with each state. So state pointer, state pointer, state pointer, state pointer, state pointer, state pointer. We'll need to pass the state pointers along to the transition. And this transition function is going to go the current state, transition out of, so we're no longer in that state anymore. And then S is going to be equal to, and it depends on what the new state is. So we'll implement all the cases. So if the new state is idle, then S is going to be equal to some new idle state, which we haven't implemented. If the case is jump, and I actually like to write my cases like this with a little break in front of them. If the case is jump, then S is going to be a new jump state, which we haven't implemented yet. And you notice that since it hasn't been implemented, we have this cyclic dependency. To fix that, we just specify that this function will have a body somewhere else, and then define it later after we've implemented all of the states. So we can go void transition and specify that this belongs to the state class. So we can define the body somewhere else. Now we can create our new jump state, and then similarly, we'll have our attack state that doesn't exist, and our all state that doesn't exist, and we can simply go S transition into now that we've switched to that new state. And this gives us the ability to implement these transition functions that define what happens when we go into and out of the states. I mentioned that these are useful for something like a player controller in a platformer, but they can also be useful for AI, so we can switch the state that an AI is in, although a lot of that has switched to behavior trees, which I should probably talk about at some point. Menus, so you can switch between different states for different levels of a menu and display different stuff based on the state of the menu. Scenes, so have a state machine that models how you transition between all the scenes in your game. So do we hit escape and transition to the pause menu, then hit go to the menu and transition to the main menu, and then hit continue and transition to the game itself? Something like that. And a whole bunch of other stuff. State machines are one of the things that my industry partners have told me that if you learn it well, can get you a job by itself. So state machines are used all over the place in games. So now we're going to talk about a fun thing. Entity component systems are kind of near and dear to my heart. A lot of what I do in my professional life is studying entity component systems. So an entity component system is a way of storing data in a game in a way that's fast for the CPU to process. So why do we want the CPU to be fast? Well, oftentimes it doesn't matter and we don't care. If we're making Flappy Birds, we don't care. We only have 100, maybe even less, 20 entities on the screen at a time. And even at the scale of something like Call of Duty, we don't care. There's probably only 100 things moving around on the map at the same time. But when we start talking about something like a particle simulation, we have 1,000,000 particles representing a destruction. Or when we start talking about an RTS game where we have thousands of little dudes running around, the CPU takes time to process all of those. And the CPU stores data in what's called a cache. So the idea with this cache is that when we fetch a byte of data, we don't actually just fetch that. We fetch all of its closest friends and relations. We fetch a line in the cache. And if something is in the cache, it's very fast to access. So CPUs have usually at least 2 levels of cache before they have to go to RAM. If something's in the first level of cache, it can almost be as fast as an addition to access it, like 1 or 2 cycles. So pretty much nothing. The next level tends to be 10 to 20 cycles. So we can do 10 to 20 additions in the time it takes to fetch the memory. And then if we have to go out to main memory, we're talking about 100 to 200 cycles. So 100 to 200 additions. So as a motivating example, if we have a simple physics function, right? So void apply physics. And we have struct entity, and it has vec3. We're going to make one of those real fast. Struct vec3, float xyz position, and it has a vec3 velocity. Then in our physics update, we can go and take an array of entities, so std span of entity. This allows us to take as many entities as we want without having to know ahead of time. Include span, std span entities, and I believe CMake would like us to go set target properties, pattern, properties, EXX standard 20. And if we give that a quick compile, it complains that there's no main function in main, but it also gets rid of the errors about span not existing. Now we can go for each entity reference in entities. We can go position, e.position equals e.position plus e.velocity. And to make this correct, float delta time times delta time. And we'll just do x, 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 and copy the code for y and z. So what's the problem with this? Well, what happens when our entity gets bigger? So we have a name, the std string name. We have maybe an acceleration, which isn't used here. We have some model pointer. We have a bunch of other stuff. Well, now we're going to assume our entity is so big that one entity fills an entire cache line. Well, in order to do this computation, every time through, we're going to have to load another cache line. We're going to miss the cache. And we mentioned that in the worst case scenario, that means that it can take up to 100 CPU cycles. And an addition takes about 1 CPU cycle. A multiplication takes 10, depending on the machine you're running on. Sometimes less, but we're going to assume 10. So we're going to assume that doing all of this is about 30 CPU cycles. Well, that means that a cache miss is the equivalent of doing, what is that? Like 4 to 6 of these operations. So we're stuck doing nothing while we wait for the memory to show up for 4 to 6 of these. So if we can avoid that waste, things get a lot better. So how can we go about avoiding that waste? Well, instead of taking an array of entities, let's instead have our entity store an array. So we're going to store a std array of vec3 100, which we're going to call positions. And we're going to do something similar for velocity, or acceleration, or the name, and so on. But we'll just go and so on. Well, now we don't care how big our entity is. All of our positions are going to be right next to each other. So they're going to fit together as closely in the cache as they possibly can. So now when we're looping over these, we have to go for, we'll take our entities, and we go for size ti equals 0, I is less than 100, plus I. We now have to go entities dot position I, positions I dot x, entities dot positions I dot x, entities dot velocity I dot x, and so on. Well, this becomes a little bit unintuitive when we have to change around the structure of our entities, right? Not every entity is going to have a position of velocity acceleration. What happens if we need to store wool is rock? What happens if we need to store a name on some of them? What happens if we have to store flammability? Well, the idea behind the entity component system is we take this idea of, instead of having arrays of structures, having structures of arrays, and makes it generic. Well, how do we do that? Well, we start making what are called components. So struct component. So we might have a position component, which is a vec3 pos. We'll put that in the right spot. We might have a velocity component, vec3 pos. And now our entity just becomes a stud vector of components data. There is one more bit we would need. So we have a bunch of components, right? So we have C1, C2, pos, right? And so we have data, 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 data. Well, now we need what's called an entity. And an entity becomes a row in all this data. So we can go, an entity is just an index, right? So our entity here would be 0, then our entity here might be 1, and so on. So we have an entity that indexes into this array of components. And entities can just be using entity equals some integer. And then there's one last part, right? Because it's an entity component system, and we've seen the entity and we've seen the component. But what does the system part look like? Well, we're already very close to having one here. So we have all of our entities, and then we loop over them, right? So this becomes an entity in the new integer sense. And so for each of the entities in our entity here, we go entities.data, right? And we pull out the appropriate component. So data, we'll call this entity, entity, entity. And we pull out the proper data for the proper component for the proper entity, and we manipulate it. So, of course, what I've sketched here won't work. Just saying components, in order to implement that effectively, is quite a bit of work. We spend 2 weeks in a undergraduate class implementing one of these. I think in the future, I will be implementing some for Stylizer, and we'll see how exactly we handle this part. It uses something called a storage usually, which takes the component and pretends that it's not typed and then imbues some type into it later. A little bit of advanced programming. It's a little bit beyond how tired I am at the moment. Cool. I'm thinking that for the next stream, we're going to try and implement a little bit of software rendering. So we'll learn a little bit more in detail how rasterization works. I'm also hoping to have a stream sometime this weekend where we implement the last few functions in our math library. Once that's done, we should be able to move on to actually drawing some stuff, which will be cool. Anyways, thank you everybody for watching. And for those of you on Twitch, I think we're gonna go do a quick little raid. Night night, thank you for watching.